Okay, so you may start.
Yun. So, good morning po again. Good morning po. Kami po ang Group 2. Ang i-report po namin ngayon ay ang measurement of earthquake and the magnitude versus the intensity.
Hello, hello. Rinig ba ako? Rinig mo ako? Sige. Okay, yun. Una is, what is earthquake? So, earthquake is defined as any sudden shaking of the ground caused by the passage of seismic waves through earth rocks. So, yun nga, earthquake ay yung paggalaw ng lupa. So, lahat naman siguro tayo ay nakaranas na ng earthquake. At alam naman natin na lindol ay isa sa pinaka-pangalib na natural disaster na naranasan ng lahat. So, yun ang earthquake ay nangyari lang kapag may seismic waves. So, seismic waves are produced when some form of energy stored in earth crust is suddenly released, usually when masses of rock straining against one another suddenly fracture and slip. So, yun, pag puno na yung energy na na-store sa ilalim ng lupa at na-release, magkakaroon na tayo ng seismic waves. So, once na karoon na ng earthquake, hindi na maiwasan ng aftershocks o pag-init. At ang pinaka-nakakatakot dito ay yung wala pang device na maaaring makadetect kung kailan ba darating or saan ba tatama ang earthquake. So, once na gumalaw ang faults na yun, doon na magkakaroon ng wave reductions. So, yun na yung seismic waves na tinatawag natin. So, madalas ay na-generate every time na nagkakaroon ng earthquake or lindol. Possible din na magkaroon ng seismic wave once na gumalaw yung tectonic plate or magkaroon ng volcanic eruption or magkaroon ng malakas na pagsabog sa ilalim or sa surface ng earth. Pwede rin. May earthquake din naman yan. Pag talagang sobrang lakas ng pagsabog niya. So yun nga, seismic waves are vibration generated by an earthquake, explosion, or similar energetic source or propagated within the earth or along its surface. So, 4 types of seismic waves. So, una, yung T waves, L waves, S waves, at yung relay R waves. So, yun. Next slide. So, ito yung picture ng seismic waves. So, 4. Bali, 2 types to na seismic wave hinati sa dalawa. Yung una ay ang body waves at surface waves. So, yung body waves ay yung nasa kaliwa at yung nasa kanan naman ay yung surface waves. At yung body waves ay dalawa, 2 types. Yung P waves at yung S waves. At yung surface waves na nasa kanan ay dalawa din. Yung L waves at yung Rayleigh waves. So, unahin natin yung body waves. Sinasabi. Ay, uy, ba? Yung P waves or yung primary waves, ito yung kauna-unahang waves na re-record ng Seismograph. Every time na lumindol. At ito yung pinaka-mabilis na mag-travel na wave. At ang wave na to, pwede mag-travel sa lahat ng medium. Ibig sabihin, pwede silang mag-travel sa solid, liquid, at gas. Pero hindi sila ganoon ka-destructive dahil ang movement nila ay alternating para silang naghihilan. So yun nga, makikita nyo yung arrow na naghihilan. So push and pull. push and pull, gano'n. So yung S waves nun, or secondary wave, ito naman yung pangalawang wave na nare-record ng seismograph. Every time na nagkakaroon ng lindol. No, ang paggalaw nito ay transverse or perpendicular. Ibig sabihin, paalon. Kung makikita nyo naman, paalon siya. Paalon ang kanyang paggalaw. Since paalon ang paggalaw niya, paalon ang paggalaw ng S waves, mas destructive ito kumpara dun sa taas yun, sa P waves. At take note na sa solid lang gumagalaw or sa solid lang pwede mag-travel ang seismic waves. So yun, ang sunod ay yung surface wave. Ito yung, unahin natin yung yung Rayleigh waves, sinasabi, yung R waves. Ano naman yung Rayleigh waves ay elliptical. Kaya kung makikita nyo, paikot siya. Parang ganyan. Paikot pero nagkakos pa rin ng up and down ang paggalaw ng lupa. At yung nastas naman yung love waves. Pero mas destructive nga to. At di hamak na mas delikado ang love waves. Ang love waves at ang love wave, ang klase ng love na hindi maganda. Dahil nga, love wave, bukod sa pag-up and down niya, possible pa din na paggalawin ito ang lupa ng side to side. Movement ng love waves. So, para hindi kayo malito, yung P waves, ang movement nito ay longitudinal, at yung S waves naman ay up and down. Tapos yung Rayleigh waves, optical, at yung love waves naman, side to side. So, yun. Next. Earthquake. Anatomy of an earthquake. An earthquake is the shaking of the ground caused by sudden motion along faults or fractures in the earth crust. Ito makikita nyo dito yung faults, epicenter, focus, or hypocenter, yung seismic waves, plates. So, yan. Yung focus ay the point within the earth where an earthquake rupture starts. So, yung focus, doon nagsisimula yung energy na magta-travel papunta dun sa taas sa epicenter. So, yung magta-travel na yun, yung seismic waves that transmit the energy released by an earthquake. Yung magta-travel dun papunta sa taas ng earth, sa surface. Tapos, yung plates naman, ito, yung dalawang plates kanina, na diniscuss. At yung fault na, yung hati, yung tissue. So, dito, seismograph, parang naman malaman kung gaano kalakas ang seismic wave, gumagamit tayo ng device or instrument na tinatawag natin seismograph. So, seismologists study earthquakes by going out and looking at the resulting damage and by looking at the records of shaking of the earth's surface caused by seismic waves. These records are obtained by the use of seismograph. So, ito nga yung seismograph, kung makikita nyo. May earth swing, frame, drum, base, wire, heavyweight, pen, and seismograph. So, yan yung ginagamit natin para mag-record tayo ng earthquake. So, seismologists yung experts pag-aaral ng mga lindol o yung volcanic eruption. So, yung seismograph ang ginagamit mga seismologists. So, yun. Para makita natin yung record ng mga lindol, dyan natin makikita yung location at magnitude ng lindol. Gamit siyang seismogram, yung seismogram na nasa yung wavegram. Yan, ginamit yung seismogram. Papel lang yung seismogram. So, pag na-record na yun, makompute natin yung magnitude at malalaman natin yung location. So, yun. Next. So, seismograph. The first seismograph was invented by the Chinese astronomer and mathematician Chang Hong in 132 AD. Ito daw yung kauna-unahang seismograph na na-invent. So, Chinese astronomer. The first true seismograph, according to the Italian seismologist, was created in 1875 by Italian physicist Filippo Cecchi. Right? So, ito yung seismogram. Ito yung nare-record natin. The record made by the seismograph is called the seismogram. Seismograms are used to determine the location and magnitude of earthquakes. And earthquakes magnitude may be considered to vary as a function of the amount of energy released. Ito yung nga sabi ko kanina, na yung seismogram ay yung nare-record ng mga lindol. So, makikita natin dito yung kung saan yung location tsaka yung magnitude. So, yan din yung P waves, S waves, tsaka yung surface waves, yung L tsaka R waves. Mas distinctive na yung surface waves kumpara dito sa body waves na P at S waves na nakikita niyo.
We know that earthquakes cause tremors on the earth. The tremors produce waves on the surface of the earth. These are called seismic waves. Seismic waves are recorded by an instrument called the seismograph. The instrument is simply a vibrating rod or a pendulum which starts vibrating when tremors occur. A pen or a marker is attached to the vibrating system. The pen records the seismic waves on a paper which moves under it. Trigger a mock earthquake on the table to see the seismograph in action. We can see that the pendulum tip records the earthquake on a graph sheet. In this activity, we have seen the recording of seismic waves caused by earthquakes.
Okay. For the magnitude of an earthquake. Magnitude of an earthquake. Magnitude is the most common measure of an earthquake size. Ito po, yung magnitude natin ay yung sukat niya, hindi po siya nagbabago sa isang lugar kahit gaano ka man, kahit gaano po kalayo yung lugar mo sa dun sa pinangyarihan ng earthquake, yung magnitude niya ay mananatili na same kumpara sa intensity na nag-iiba. Depende sa layo mo sa lugar ng earthquake. It is an objective parameter that measures either energy radiated by or moment released in the earthquake source does not reflect macroseismic effects. Tapos, meron po tayong tatlong commonly used na magnitude scales. These are the local magnitude scale, surface wave scale, and the moment magnitude scale. Meron ito po yung tatlo na karaniwang ginagamit na scale natin. Pero karamihan po sa atin parang ang alam po lang po natin tungkol sa magnitude ay yung dun sa Richter scale. Pero yun po ay, yung Richter scale po, isa po yun dun sa pinakaunang ginagamit. Pero ngayon pong sa pag-advance po ng mga technology, naka-develop po tayo ng bagong paraan para ma-measure yung yung magnitude ng earthquake natin. Next po. So the first one is the local magnitude scale. It is also known as the Richter scale. It is a quantitative measure of an earthquake magnitude devised by Charles Richter in 1935. Yon, ito pong local magnitude scale ay yung pinakaunang na-develop na paraan ng pagsukat natin ng earthquake o yung mas kilala natin bilang Richter scale. Ito po ay originally dinivide siya para ma-measure yung mga maliliit lang na earthquakes tsaka yung malalapit lang na nangyaring earthquake doon sa mismong seismograph natin or yung nagre-record ng mga seismic waves. Next po. Yon. Si Charles Francis Richter or yun nga po, siya nga po yung nag-devise ng ating Richter scale together with Ben Gottenberg, ay German-born Caltech professor. Yun po, based on instrumental recording of ground motion, it provided a quantitative measure of earthquake size and complemented the older Mercalli scale. Yun po, ibig sabihin po, noong kasing yung mga unang panahon na wala pa tayong scale na para i-measure yung size ng earthquake natin, ang pagparaan lang po para ma-describe natin yung earthquake ay based sa damage na nakakalculate or na po-produce ng earthquake. Yun nga po yung yung Mercalli or scale or yung kilala natin bilang intensity scale. Next po. Yon, meron po tayong formula para makuha yung magnitude scale, local magnitude scale. Ito po ay yung ML or the local magnitude scale is equal to log of A minus log of A sub 0. Or pag dinerive po natin yan, pag sinimplify po natin yan, di ba po ang isa sa property ng logarithm, pag pinag-minus po natin yung dalawang logarithm na same base, ay equivalent din po siya sa log of A over A sub 0. Kung saan po yung A natin ay yung maximum trace amplitude in millimeter as recorded by Standard Wood-Anderson Seismograph. Yun po yung A ay mamaya po makikita po natin dun sa example natin. Tapos po, yung A sub 0 is 0.001 millimeter. This corresponds to the smallest earthquake that can be recorded. Next po. Ayun po, ito po yung approximate correlation between local magnitude and peak ground acceleration during shaking. Makikita po natin doon sa table yung pong magnitude natin na less than or equal sa 2, tapos po yung mga data po natin dito from 5, 6, 7 and greater than 10, yung acceleration po niya during the shaking po. Next po. Ayun, ito po yung yun po dun sa kaninang formula, ano po, parang medyo unreliable po siya pagdating po sa mga larger magnitude scale dahil po yung distance po nung ating station mula dun sa epicenter ng earthquake ay limited lang po. Dapat may exact proximity lang po mula dun sa mismong epicenter. Ito po yung isang ginagamit natin na paraan para ma-measure yung magnitude ng earthquake gamit yung Richter scale. Ito nga po yung, kung makikita po natin yung drawing natin or yung seismogram, yun po yung amplitude na equals 23 millimeters. Ito po yung kaninang tinutukoy na A. Yung maximum amplitude po niya nung secondary waves. Tapos po yung S minus P equals 24 seconds, kung makikita po natin, yun po yung time interval na dumaan yung time interval po ng pagdating ng P waves and S waves. Yun po ay tinatawag din natin na lag time. Tapos, dito po meron po tayong tatlong parang scale. Yun po na sa pinakakaliwa, yun po ay distance ng ating station na nag-record ng seismogram dun po sa mismong epicenter. Tapos yun naman pong gitna, yung mismo nating Richter scale. Tapos yung nasa pinaka-kanan po ay yung scale ng amplitude natin in millimeters. Next po. Yan po. Papakita po natin kung paano na minemeasure yung magnitude ng Richter scale gamit po yung tatlong scale na pinakita.
How to determine an earthquake's Richter magnitude. In 1935, geologist Charles Francis Richter devised a system known as the Richter Scale. This scale measured the energy output of earthquakes, ranging from a value of 1 for the weakest earthquakes up to a value of 10 for the strongest. You can see the scale here. In this video, I'd like to show you how we go about calculating the Richter magnitude of an earthquake. To begin, we must have a seismogram. So imagine for a moment you're sitting at a seismometer and an earthquake happens somewhere in the world and your seismometer gets this reading. So let's do some analysis of this seismogram. First of all, the first jump is always going to represent the arrival. How to determine an earthquake's Richter magnitude. In 1935, geologist Charles Francis Richter devised a system known as the Richter Scale. This scale measured the energy output of earthquakes, ranging from a value of 1 for the weakest earthquakes up to a value of 10 for the strongest. You can see the scale here. In this video, I'd like to show you how we go about calculating the Richter magnitude of an earthquake. To begin, we must have a seismogram. So imagine for a moment you're sitting at a seismometer and an earthquake happens somewhere in the world, and your seismometer gets this reading. So let's do some analysis of this seismogram. First of all, the first jump is always going to represent the arrival of the P wave, or the primary wave, and the second jump is going to represent the arrival of the secondary wave, or the S wave, seen here. This line is what we call the baseline, and that's what we're going to compare the height of the waves to. We can see that there has been a 30-second difference in the arrival of the P wave and the S wave on this particular seismogram. We call that time the lag time. Additionally, we will need a scale that tells us how high the highest S waves reached for this particular earthquake. In this example, we'll say that the highest S wave reached a height of 23 millimeters above the baseline. Now, before we can calculate the Richter magnitude, we need to do a little bit of work. And the first thing we want to do is figure out how far away from the earthquake's epicenter our location is. And to do that, we need to look at the lag time, which in this case is 30 seconds. Let's pull out our travel time chart and a piece of scrap paper and mark off that lag time. All we need to do now is wedge it in between the two curves until it fits, at which point we go down the edge of our scrap paper and notice that the distance is 210 kilometers. Let's add that to the list of information we know. Now, in order to find the Richter magnitude, we will need that epicenter distance, and we'll need one other piece of information, which in this case is the height above the baseline, ours being 23 millimeters. So let's keep those two pieces of data in mind, and let's bring in the chart we need to calculate the Richter magnitude. It's kind of a bizarre looking chart. Let me show you how it works. Notice I've color-coded our pieces of data. So the pink dot is going to represent our epicenter distance, which we calculated to be 210 kilometers. And our blue dot is going to represent the height of the largest S wave, which in our case was 23 millimeters above the baseline. We simply need to plot those 2 points on the left and right axis of this chart as such. You'll notice the pink dot is at a distance of 210, and the blue dot is at a height of 23. Now all we need to do is use a straight edge to connect those 2 points. And wherever we cross the middle axis, the Richter magnitude axis, that is our Richter magnitude. So this earthquake has a Richter magnitude of 5.0. And that's how you calculate the Richter magnitude for an earthquake. Determining the epicenter distance using the wedge method. Imagine for a second you're sitting by a seismometer, and all of a sudden it starts to shake, signifying that an earthquake has taken place. You want to know just exactly how far away that earthquake was. Well, we could do this simply by looking at the report printed out by our seismometer. This is called a seismogram. Now, with a little bit of analysis, this simple diagram can show me how far I am from the epicenter. Here's how it works. First thing we want to look at is the first moment when the seismogram jumps. That signifies the arrival of the P wave. The second significant jump signifies the arrival of the S wave. Now, if we want to know how far we are from the earthquake, how far apart those two arrivals are can reveal that. So what we need to do is a little bit of simple math. We need to calculate something known as the lag time, which is simply the difference between the arrival of the P wave and the arrival of the S wave. Now, in this example, the P wave seems to have arrived at about 9:08 and the S wave at about 9:15. And that would give us a difference in arrival time, also known as a lag time, of 7 minutes. Let's keep that number in mind and take a look at our reference tables. Now, we're going to use a method known as the wedge method to figure out just how far away an earthquake is that would have a lag time of 7 minutes. To do that, we need some scrap paper. And what we'll do is we'll take our scrap paper and we'll align it with our vertical axis, or our travel time axis, on our reference table. And we're going to go ahead and mark off the lag time, which in this case is 7 minutes. I like to make a mark at 0 and a mark at 7, and I also like to label it just to make it very clear. Now, the reason this method is called the wedge method is because once we have the lag time marked, we're going to wedge it in between the two travel curves, the P curve and the S curve, until it lines up perfectly, keeping in mind that the scrap paper needs to remain perfectly vertical. Try and use the grid lines to help keep it in line. Once you have it lined up with the two curves, you simply follow that piece of scrap paper down to the bottom, and that will reveal the distance to the epicenter, which in this case appears to be about 5,400 kilometers. So by simply looking at the lag time and using our reference table, we can figure out how far away we are from the earthquake epicenter. Something neat is true though. We can actually do the same problem backwards. Here's how that would work, and I'm going to use different numbers. Let's say we're faced with this question. A seismic station is 2,000 kilometers from the epicenter of an earthquake. How far apart will the arrival of the P waves and S waves be? So in this example, I'm giving you the epicenter distance and asking you to work backwards to find the lag time. Let's see how we would do this. Keep in mind that our distance in this case was 2,000 kilometers. So I'm going to locate that on the epicenter distance axis of my reference table. Now again, I'm going to grab some scrap paper and line it up on the 2,000 kilometer line as such. Just like we did, but backwards, we're going to mark where the two lines are. And then we want to know how far apart those are, and that will give us our lag time. So I'm going to take it and slide it back down to the travel time axis. And however far apart they are is our lag time. In this case, it appears to be about 3 minutes and 20 seconds. So that's how we can use a seismogram to find distance, or backwards, we can use distance to find a lag time. This is a very important skill for the New York State Earth Science Regents exam, so make sure you practice.
Wait lang po, nagkakaproblema lang po sa Seismic. So, yun nga po yung nakita po natin yung pag-calculate po ng epicenter distance gamit po yung lag time natin. Ito po yung example ng chart ng earthquake P wave and S wave travel time. Dito po sa sa y-axis natin ay yung time natin in minutes, tapos sa ating x-axis yung distance in kilometers. Yan po, ito pong method na to ay ginagamit nung earlier times po, nung wala pa tayong masyadong advanced na method na ginagamit sa pagsukat ng magnitude. Kaya po, nung nakita nyo po ay medyo manual po yung ating computation. Next slide po. So, ito nga po yung Richter scale natin. Yung table natin, makikita natin yung magnitude, tapos yung description at yung effects niya. Ito pong mga magnitude between 0 to 2.0, ito po ay halos araw-araw po ay may nangyayaring earthquakes na ganito yung magnitude, hindi lang po natin nararamdaman. Ang nakakaano lang po niyan ay yung ating mga seismograph stations. Tapos ito po, yan, makikita natin yung effects ng mga earthquake na to. Kung makikita po natin dito sa pinaka-maximum natin na 10 plus, hindi pa po tayo nakakaranas ng ganitong earthquake. Next slide po. Sunod naman po ay yung surface wave magnitude scale or yung symbol natin na M sub S. Yung surface wave magnitude scale is based on the maximum amplitude of the surface wave having a period of 20 plus 2 seconds. It is used for observations near the earthquake epicenter where the surface wave is higher than the body wave. This scale applies to any epicentral distance or type of seismograph. Hindi po, kagaya po dun sa kanina na local magnitude scale, na meron lang pong specific distance mula dun sa epicenter ng earthquake papunta dun sa station na kailangan. At meron lang pong standard na seismograph na ginagamit. Dito naman po, kahit anong distance natin mula dun sa earthquake, ma-measure po natin yung magnitude. Yun po ay gamit yung formula na M sub S is equal to log of A prime plus 1.66 log of delta plus 2.0, where MS is the surface wave magnitude scale, A prime is the maximum ground displacement. It is measured po in micrometer. Tandaan niyo po yung micrometer. Tapos yung delta natin is epicenter distance to seismograph measured in degrees. Ito po ay yung measure na delta, in degrees po natin siya sinusukat. Mamaya makikita po natin sa example. This magnitude scale is typically used for moderate to large earthquakes having shallow focal depth. Furthermore, seismograph should be at least 1,000 km from epicenter. Next po. Yan, ito po yung example problem natin. Assume that a seismograph located 1,200 kilometers from the epicenter of an earthquake records a maximum ground displacement of 15.6 millimeters for surface waves having a period of 20 seconds. Based on these assumptions, determine the surface wave magnitude. Yun nga po yung formula po natin kanina, itong MS is equal to log of A prime plus 1.66 log of delta plus 2.0. Kung saan, yung distance po natin mula sa seismograph station papunta dun sa epicenter ng earthquake ay i-measure natin in degrees. Para po makuha yun, kailangan po natin yung circumference ng earth na approximately 4.0 times 10 raised to 7 meters. Tapos po, alam naman po natin na ang isang buong circumference ay 360 degrees. Ang gagawin po natin, yung delta natin, yung distance natin mula sa seismograph in kilometers, i-convert muna natin sa meters. which is 1.2 times 10 raised to 6 meters. Tapos i-divide po natin siya sa circumference ng Earth, which is 4.0 times 10 raised to 7 meters. Tapos itatimes po natin siya sa 360 degrees. Yun po, yung distance po natin mula sa epicenter papunta sa seismograph ay 10.8 degrees. Tapos po, yung A prime natin, sinabi naman po dito sa problem na maximum ground displacement of 15.6 millimeters. Sabi po sa atin kanina, ang unit na kailangan natin ay micrometers. Yung millimeters, pag kinonvert po natin sa micrometers, itatimes lang po natin ng 1,000. Kasi po, milli, di ba, ay 10 raised to negative 3, tapos ang micro ay 10 raised to negative 6. Kaya po, pag kinonvert natin, magiging 15,600 micrometers. Yun po, ngayon mayroon na tayong mga kailangan natin data. Meron na po tayo. Pwede na natin i-substitute sa formula natin na m sub s is equal to log of a prime plus 1.66 log of delta plus 2. Yun equals to log of 15,600 plus 1.66 log of 10.8 plus 2, which is equivalent to 7.2. Yun po. Sunod naman po natin ay yung moment magnitude scale. Ay, pakibalik nga po dun sa, yun po, i-familiarize nyo lang po sandali. Baka po, sabihin nyo po pag okay na. Yun siguro pwede na. Next slide na po. Yun naman, ang sunod naman natin ay moment magnitude scale. The moment magnitude scale is a measure of an earthquake's magnitude or the size or strength based on its seismic moment. Moment is a physical quantity proportional to the slit on the fault multiplied by the area of the fault surface that slits. Yun nga po, sa moment magnitude scale naman, ang una po natin kailangan hanapin ay yung tinatawag na seismic moment. Yung seismic moment po natin ay may symbol na M sub O. Yun po ay may formula na M sub O is equal to mu times A sub F times D. Ang unit po niya ay Newton meter. Yung mu po natin ay yun po ay yung shear modulus of material along fault plane in Newton per meter squared. Yun po ay constant po. Meron po tayong value na 3 times 10 raised to 10 Newton per meter squared para sa cast natin. Tapos meron naman po tayong 7 times 10 raised to 12 Newton per square meter para sa mantle. Ito pong mu natin ay yung tinatawag din po nating rigidity of rock. Kaya po mas mataas yung value ng ating mu sa mantle kaysa sa cast dahil po ang isa po sa characteristic ng seismic waves ay mas mabilis po siya mag-travel sa mga, di ba, mabilis po siya mag-travel sa solid natin na materials. Yung mantle po natin ay mas dense kaysa sa cast natin. Kaya po, mas malaki po yung value ng shear modulus. Yun naman pong A sub F equals area of fault plane undergoing slip measured in square meter. Ito po ay yung length ng surface rupture times the depth of aftershakes. And D naman po is average displacement of ruptured segment of fault measured in meters. Pag nakuha na po natin yung seismic moment, pwede na po natin makuha yung moment magnitude scale, which is the M sub W. Na may formula po na M sub W is equal to 2/3 log of M sub O minus 6. Next slide po. Ayan po, para mas maintindihan po natin yung
Earthquakes are now reported as moment magnitude. So what happened to the Richter scale? Charles Richter and Benno Gutenberg developed the first magnitude scale in the 1930s to quantify earthquakes by relating the size or amplitude of seismic waves, shown on the right, plotted against distances calculated from S minus P arrival times, shown on the left. Connecting the two gives you the Richter magnitude. The scale is logarithmic, so a 1 unit increase in magnitude corresponds to 10 times larger amplitude. The limitation was that seismologists measured certain frequencies, which meant that the signals from large earthquakes weren't adequately represented, like not being able to hear the bass notes on your laptop speaker. That meant that the Richter scale underestimated the size of large earthquakes. Seismologists have since developed far more sensitive seismometers that, with faster computers, have enabled them to record and interpret a broader spectrum of seismic signals. These improvements allowed them to better determine the energy released by large earthquakes. In 1979, they connected the seismograph recordings with the actual physical displacements that occurred during an earthquake. The result was the moment magnitude scale. Seismologists no longer look at only the amplitude of seismic waves, but instead use much more information contained in the seismogram to calculate what is called the seismic moment. The seismic moment, which defines how much force is needed to generate the recorded waves, is defined by this equation: mu times distance times area. Mu is rock rigidity. It describes the resistance of the rock to bending when force is applied and is a constant for a given rock material. More elastic energy is stored bending rocks of high rigidity than is stored bending rocks of low rigidity. For example, this brick has high rigidity, and when bent or sheared, would yield a strong earthquake. The cake has lower mu and shears easily. Rock rigidity is lower in the crust than it is in the mantle. As mentioned earlier, in most cases, distance and area can be determined by mathematical modeling of seismograms. D is the distance that the rock slipped along one side of the fault zone relative to the other side. In the 1906 San Francisco earthquake, this fence line was offset over 3 meters. A is the estimated area of the fault zone along which the rock slipped, the distance D. It defines the area that actually ruptured during the earthquake. Let's watch an earthquake happen. The arrows show forces building on opposing sides of a fault. Growing stress that will be relieved in the earthquake will be shown in red. Here we see blocks of rock move in opposite directions along a strike-slip fault zone, such as the San Andreas Fault in California. Potential energy, in the form of elastic energy, is stored in Earth's crust or mantle, building stress as the ground slowly deforms between large earthquakes. Take a look below the ground at the earthquake rupture that defines the seismic moment. That equation is then plugged into the moment magnitude equation, which is used by seismologists to measure the size of earthquakes in terms of the energy released, not just the amplitude of the recorded waves. The constants in the moment magnitude scale are chosen such that at smaller magnitudes, the moment magnitude matches the Richter scale. To truly appreciate this, consider the changes in the earthquake rupture required to increase the moment magnitude by 1 unit. Either the area of rupture or the slip distance, or both, must increase so that the product of slip distance times area increases by a factor of 32. While the amplitude of shaking caused by a magnitude 5 earthquake is 10 times larger than for a magnitude 4 earthquake, the energy released increases by about 32 times for each unit increase in magnitude. To understand the scaling, we'll look at the effects of the rupture area by using pasta as a model for magnitude. The cross-sectional area of a strand of spaghetti is about 1 square millimeter. When you break the noodle, it makes an earthquake of, let's just say, magnitude 5 for our model. mu is constant for all strands of pasta, and for d, we'll use 1 millimeter of displacement across the fault. So here we see the pasta break and move laterally 1 millimeter. To increase it to a moment magnitude of 6, we multiply it times 32. The surface area is 32 times higher, yet the amplitude is just 10 times higher. To reach a magnitude 7, you have to multiply 32 times 32, and you get roughly 1,000 strands, or about a pound of spaghetti noodles. To get a magnitude 8, you need 32,000 pieces of spaghetti. A magnitude 9, on the other hand, would require 1,000,000 pieces of spaghetti. A magnitude 9 releases 1,000 times more energy than a magnitude 7 earthquake.
I-back mo pa. Yung isa. Ano na? Wait lang. Yun po. Hindi lang po napasama diyan sa slides. Pero meron pa tayong isang formula na kailangan tandaan. Yun ay yung energy released by an earthquake, which is denoted by capital letter E. Isulat nyo na lang po sa papel. Letter E can be roughly estimated by converting the moment magnitude to energy using the equation. Log of E is equal to 5.24 plus 1.44 m. Isasend ko po sa chat box yung formula. Nandun po sa chat natin. Log of E is equal to 5.24 plus 1.44 m. Kung saan po yung E ay yun po yung energy natin in joules po siya na ang unit niya, joules. Tapos yun naman pong M, yun po yung moment magnitude natin. Then for the example problem, assume that during a major earthquake, the depth of fault rupture is estimated to be 15 kilometers. The length of the surface faulting is determined to be 600 kilometers, and the average slip along the fault is 2.5 meters. Based on these assumptions, determine the moment magnitude. Use a shear modulus equal to 3 times 10 raised to 10 Newton per square meter. Ibig sabihin sa CAS po siya nag-occur. Yon. Meron po tayong formula. Sabi nga po natin kanina, ang una po natin kailangan hanapin ay yung seismic moment. Para makuha po natin yung seismic moment, may formula tayo ng mu A sub F times D. Yung mu natin, given na po na 3 times 10 raised to 10. Tapos yun naman pong area natin, meron po tayong binigay na yung dimensions po natin na 15 kilometers by 600 kilometers. Pag minultiply po natin yung dalawa, magkakameron po tayo ng 9,000 square kilometer na area. I-convert po natin siya sa square meter. Yung 9,000 square kilometer ay equivalent to 9,000, 9 times 10 raised to 9 square meter. Tapos yun naman pong yung delta naman po natin or yung D, yun ay yung 2.5 meters. Yung given po na average slip along the fault is 2.5 meters. Nagkamali lang po ng yon. Mako-compute na po natin yung seismic moment na mu AD. Substitute lang po natin 3 times 10 raised to 10 times 9 times 10 raised to 9 square meter times 2.5 meters. Magkakameron po tayo ng 6.75 times 10 raised to 20 Newton meter. Yun po yung seismic moment. Alam naman po natin na ang unit ng moment ay force times the distance. Tapos, yun naman po, dahil meron na tayo ng seismic moment, makakompute na natin yung moment magnitude. Na may formula po kanina na 2/3 log of m sub o plus minus 6. Dito lang po ay ginawang 0.67 yung 2/3. Tapos, yun nga po, substitute lang po natin yung value ng m, magiging negative 6 plus 0.67 or 2/3 log of m sub o. Magkakameron po tayo ng value na 8. Yun po, familiarize nyo lang po ng konti yung process natin. Okay na, sige. Ay, pabak mo na. Pabak. Ayan, meron na. Ngayon po, meron tayo nung quiz natin. Simple lang po ang rules ng quiz natin. Yung una pong makakapag-send ng tamang sagot sa chat, sa comment section natin, siya po ay magkakameron ng prize po. Na kukuha niyo po ba? Yun po, sana ay tinandaan niyo po yung mga process ng pagsasolve natin kanina. Ready na pa? Ready na? Paraisan niya po kung ready na kayo. Ayan. So, para sa una nating tanong, next. Yan. Assume that a seismograph located 1,000 kilometers from the epicenter of an earthquake records a maximum ground displacement of 24.5 millimeters for the surface waves having a period of 20 seconds. Based on these assumptions, determine the surface wave magnitude. Go na po. Wala po pong nakakapag-send doon sa Yes po.
Try lang po.
Chat po sa
8
comment section.
8.37.
Hindi po. Wala pong mag-session ng sagot. Sige po. Yun, meron na pong nauna na nakapag-send. Ang tama pong sagot ay 7.973 or 8 po pag ating in-round off. Pakita po natin yung kung paano sinolve yung problem. Next slide. Next slide po. Yan. So, yun po, yung formula natin ay yung log of A prime plus 1.66 log of delta plus 2. Kung saan nga po sabi ko kanina, yung delta natin ay kailangan naka-degrees. I-convert po natin siya to degrees. Para gawin yon, yung distance natin in kilometers, i-convert natin sa meters, then i-divide natin doon sa circumference ng Earth times 360 degrees, which is equal to 9 degrees. Tapos yung A prime natin na given ay 24.5 millimeters. I-convert po natin siya sa micrometers na equivalent po niya ay 24,500. Tapos, direct sub lang po sa formula natin, magiging log of 24,500 plus 1.66 log of 9 plus 2 is equal to 7.973 or 8. May tatlo pa po tayong tanong, pwede pa po kayo makabawi. Next question po. Yun, para sa question to natin, assume that during a major earthquake, the depth of full rupture is estimated to be 15.6 kilometers. The length of surface faulting is determined to be 630 kilometers, and the average slip along the fault is 3 meters. Based on these assumptions, determine the moment magnitude. Use a shear modulus equal to 7 times 10 raised to 12 Newton per square meter. Moment magnitude naman po ang hinahanap. Hindi po 5.50 po. Yan, may nakatama na po. Si Miss Joyce Lorena po. 9.543 ang correct answer. Pakita po natin yung solution. Yan. Yung base nga po sa formula natin na mu A sub F times D. Ang mu po natin ay given na 7 times 10 raised to 12. Tapos ang area po natin given yung 15.6 kilometers times 630 kilometers, which is 9,828 kilometers squared. Pag kinonvert po natin siya sa square meter, magiging 9.828 times 10 raised to 9. Tapos yung given po natin kanina na D ay 3 meters. Tapos substitute lang po natin, makukuha natin yung moment, seismic moment na 2.06388 times 10 raised to 23. Tapos substitute lang po natin sa formula ng moment magnitude na 2/3 log of m sub o minus 6. At makukuha po natin yung sagot na 9.543. May dalawa po tayong tanong. Next problem po. Yan. The standard Wood-Anderson's seismograph has a natural period of 0.8 seconds, damping factor of 80%, and static magnification of 2,800. It is located exactly at 100 km from the epicenter. Maximum phase amplitude recorded by it is 14.9 cm. Determine the Richter magnitude. Pabilisan lang po, isa po sa pinakamadaling problem. Ayan, may nauna na po ang si Miss GB Manalo. Ang sagot po natin ay 5.17 or 5.2. Pakita po natin yung solution. Yun po. Sabi nga po kanina, ang formula po ng Richter magnitude or the local magnitude M sub L is equal to log of A over A sub O. Na yung A po natin kailangan naka-millimeters. Ang given po sa atin ay 14.9 centimeters. Convert po natin siya sa millimeter ay 149. Tapos yung A sub O, standard po siya na 0.001 millimeters. Yun po, substitute lang, makukuha po natin yung magnitude natin. Last problem po natin. Yan. Sana po natandaan niyo yung formula ng energy. If the moment magnitude of an earthquake is 8.2 on Richter scale, calculate the energy released by the earthquake. Nandito po sa comment section yung formula. Pabilisan na lang. Mali po yung 17.04. Ayun, may nakakuha na po. Ang tamang sagot po ay 1.12 times 10 raised to 17. Joules po, joules. Pakita po natin yung solution. Yun. Yun nga po, may formula tayo na log of E is equal to 5.24 plus 1.44 M. Yung M po natin given na 8.2. Then, substitute lang po natin sa formula, log of E equals 5.24 plus 1.44 times 8.2. I-shift solve nyo lang po sa calculus, lalabas po ay E equals 1.12 times 10 raised to 7. Next po, bago po natin putulin yung yun lang po, isang trivia lang po. What is the highest magnitude of earthquake ever recorded? The largest earthquake ever recorded in real life struck central Chile on May 22, 1960 with a magnitude of 9.6 or sa karamihan po ay 9.5 po itong magnitude. This was a truly massive quake, more than twice as powerful as the next largest in Alaska in 1964 and 500 times more powerful than the April 2015 Nepal earthquake. The seismic energy released by the 1960 Chile quake was equal to about 20,000 Hiroshima atomic bombs. Thousands were killed. It also triggered a tsunami that traveled 17,000 kilometers across the Pacific Ocean and killed hundreds in Japan. So hanggang dito na lang daw po muna. Tuloy na lang po natin.
Okay, so thank you do sa ating mga reporters na nag-present today. For the second group, meron pa silang topic. I think it's the difference between the magnitude and intensity. Okay, so ito is another interesting topic dito sa report nila. And ang comment ko, same as for the group 1, especially yung inyo, ayan, may present nga ayun ng mga equation and formula. Kasi hindi nyo naman kasi kailangan din yan sa uluhin. Ang akin lang, at least alam nyo yung proseso or may idea kayo kung paano kino-compute. Again, ito naman is, hindi naman kayo mag-seismologist, di ba? So, kumbaga lang, familiar lang kayo doon sa ano. So, good effort. At least, inalam nyo yung process ng pagsosolve, yung mga surface wave magnitude, yung mga moment magnitude, saka yung mga energy. Ayan. So, good job. And then, ayun nga, continuation ng report nila. So, alamin natin what is the difference between magnitude and intensity. So, ito yung usually dalawang term na madalas nating naririnig kapag may mga earthquake na nangyayari. Ano? So, binabrowse ko tong report nila. May mga videos din. So, good job. At least may rin. Yung mga videos na present ko nung una. Very interesting din. Okay? So, ang tawag dito? Sige, next week na lang. Mag-quiz siguro tayo para do sa dalawang topic na ni-report. And then, sit work lang. So next week, that will be quiz for the first two report. And then the remaining time will be used for a sit work. Okay, so far so good. Thank you. Thank you sa mga nag-report. And yun lang. See you guys next week. You may now leave the gym room.
Thank you po.
Thank you, sir.
Thank you po, sir.
Thank you po, sir.
Thank you po, sir.
Thank you po, sir.